If you build web applications, you have seen this red text. A fetch request fails, the console lights up, and you are staring at a cross-origin resource sharing, or CORS, error. The immediate instinct is to assume the API endpoint is broken, misconfigured, or offline, but that is rarely the case. The target server is usually fine. That red error is actually your very own browser stepping in to prevent your code from reading the network response. To understand exactly why the browser intervenes, we have to look at the web's baseline security perimeter, the same origin policy. An origin is a specific combination of three variables: the protocol, the host, and the port. Change even one of these, like moving from HTTP to HTTPS, or requesting an API on a different subdomain, and you cross the boundary. The same origin policy exists, so a malicious script on one website cannot execute unmediated network calls, accessing private data from a different domain. But modern architecture requires crossing that boundary. Single-page applications are built to fetch data from decoupled microservices, third-party APIs, and diverse subdomains. Browser engines have to expose robust HTTP capabilities to your JavaScript, but they cannot punch holes in the same origin isolation perimeter to do it. To bridge this gap, browsers enforce a hidden architectural negotiation protocol before they ever transmit your complex payloads. Mapping out this hidden execution timeline step by step provides the technical clarity needed to debug these failures at the protocol level. Before we look at the negotiation protocol, we need to define how legacy network calls bypass it entirely. This sequence diagram maps a simple request, utilizing legacy HTTP methods like GET or POST and standard form data headers. When your JavaScript thread initiates a simple request, the data payload moves directly through the browser's network API and out to the target server. Passing through, the browser automatically stamps the packet with an origin header. Your JavaScript does not instruct this. The engine enforces it. The target server receives the payload, processes the request, and returns data, attaching an access control allow origin header to its response. Here is the catch. Your JavaScript does not get that data yet. The browser's network API stops the packet and scans that allow origin label. If the server's label matches the client's origin, the browser hands the response up to the call stack. If it doesn't match, or if the header is missing, the browser obfuscates the payload. The vulnerability here is obvious. With a simple request, the server-side data mutation happens before the browser ever validates the cross-origin permissions. That retroactive check is too dangerous for modern API architecture, so when you upgrade your fetch request with modern parameters, the browser alters its execution strategy. Setting the content type to application.json, attaching an authorization header, or using HTTP verbs like put or delete will trigger this shift. Injecting any of these parameters reclassifies the network call as a preflighted request. The moment you execute that code, the browser engine steps in and refuses to transmit your payload over the network. Your JavaScript thread is not blocked. Instead, the fetch promise is held in a pending state in the microtask queue, while the browser's network API lane locks down. The browser temporarily decouples from your application logic and takes autonomous control of the network layer. Allowing a complex, unverified mutation payload to hit a foreign server blindly is a security risk. The browser must ask for permission first. To get that permission, the browser engine generates a lightweight HTTP options probe and fires it at the target server. It leaves your actual data behind, but attaches two pieces of metadata to the probe: the access control request method and the access control request headers. The browser is explicitly asking the server, do you support these specific HTTP methods and custom headers, and do you accept them from my origin? The target server now has an architectural responsibility. It must evaluate those incoming parameters and reply with explicit opt-in headers. A properly configured server evaluates the probe and replies with access control allow methods and access control allow headers. The server transmits this permission slip back across the network, handing it to the browser engine for evaluation. This pre-flight handshake acts as a mandatory zero-trust negotiation layer between your client scripts and the foreign server they want to talk to. The browser reads the server's return headers. If the allowed methods and headers perfectly match the parameters of your pending request, the check passes. The network API unpauses, the padlock opens, and the browser finally transmits your original, complex fetch payload. Once the server processes that actual payload and returns the final response, the pending promise in your microtask queue resolves, handing the data back to your JavaScript. But consider the failure condition. If the server omits the required headers or rejects the origin during the options probe, the negotiation fails. The browser's mitigation protocol is immediate. It blocks the connection and destroys your pending payload before it touches the network. Your JavaScript promise is forcibly rejected. The application logic remains isolated from the network layer. That red CORS console error is simply the terminal output of this failed pre-flight negotiation. It means the browser did its job. This side-by-side waterfall chart shows the macroscopic execution timelines of the two request types. The physical system design cost of this security becomes obvious. A pre-flighted request doubles the network round-trip latency. Every API call requires an extra round trip just to ask for permission. In production, this overhead penalizes your performance budgets and degrades core web vitals. To mitigate this latency, system architects implement an optimization, caching the pre-flight. When the server responds to the initial options probe, it can issue an access control max age header alongside its permissions. This header instructs the browser to remember the permissions for a set number of seconds, skipping the options probe for identical future requests to that endpoint. With the cache active, your complex, pre-flighted requests execute with the exact same speed as a simple request. The CORS pre-flight is a security handshake. It enforces the web's baseline isolation boundary while giving developers the tools required to build complex, distributed networks.